Now let's consider entropy, defined in this equation scientifically by the capital letter S, the Boltzmann constant, and the logarithm in natural form of the number of independent microscopic states. Well, let's unpack that in a little more detail to make it easier to understand. At the microscopic level, there is no arrow of time in the fundamental laws of nature. They're time reversible. Pretty much exclusively we've seen in interactions between simple objects, especially subatomic particles. They're perfectly reversible. Whatever interaction you see flowing forward in time could equally well occur backwards in time. The arrow of time apparently only emerges when there are many moving parts. Look at this sequence of images, and you can tell intuitively, without thinking of entropy or physics, what is the more or less likely situations, or if there was a time evolution, in which way it would go. Imagine these as particles in a room or billiard balls on a table, and as time passes, it's clear that C is the most specific and in general the most unlikely configuration. With more interactions and more time passing, they will obviously become more uniformly distributed through the space. So in that sense, B is also an unlikely configuration, and D is somewhat less likely. A is the most likely configuration here. So if we imagine a time passage, it would go from C to D to B to A. Here's an example with two different gases, or two different types of particles, billiard balls on a table if you like. And again, the same idea applies. The most separated and unlikely configuration is D. It would have to be arranged that way. As the billiard balls or particles or atoms move around, they will mix. So the next most unlikely configuration is B, and then A or C. So without knowing anything about this system, we can say what the most likely configuration is, and if time is flowing with interactions, what the time evolution is likely to be. Here's a dynamic version of this, where two gases are separated by a barrier, and they're color-coded particles to distinguish them, and as the barrier is removed, the two gases mix. The arrow of time is obvious here. We would never see this played out in reverse. And we know intuitively why, but physicists can put their finger on why that is in a more fundamental sense. Look at this, for example. One sequence of events we can definitely notice in everyday life, ice cubes melting into water, but we never see the other. Is it because water can never cool to the point of freezing? Well, we can make that happen all the time in a freezer or refrigerator. But water in frozen form is more organized and regular, ice crystals, whereas water molecules are moving around and milling in a liquid. So in terms of disorder or entropy, one of these sequences is a progression to higher disorder, and the other is going against entropy, and so is less likely to be seen. And so we have the general idea of order flowing towards disorder and the past and the future flowing from this. If you doubt how obvious it is for certain things to play only asymmetrically in one direction where the reverse would never be seen, take a look at the following unlikely set of events.
Working all day for a mean little man with a clip-on tie and a rub-on tan. He's got me running around the office like a dog around a track. But when I get back home, you're always there to rub my back. Hey Julie, look what they're doing to me, trying to trip me up, trying to wear me down. Julie, I swear it's so hard to bear it, and I'd never make it through without you around. No, I'd never make it through without you around. Hours on the phone making pointless calls. I got a desk full of paper that means nothing at all. Sometimes I catch myself staring into space, counting down the hours till I get to see your face. Hey Julie, look what they're doing doing to me, trying to trip me up, trying to wear me down. Julie, I swear it's so hard to bear it, and I'd never make it through without you around. No, I'd never make it through without you around. How did it come to be that you and I must be far away from each other every day? Why must I spend my time filling up my mind with facts and figures that never add up anyway? They never add up anyway. Toupee and a soup-stained tie. He's got me running around the office like a gerbil on a wheel. He can tell me what to do, but he can't tell me what to feel. Hey, Julie, look what they're doing to me, trying to trip me up, trying to wear me down. Julie, I swear it's so hard to bear it, and I'd never make it through without you around. No, I'd never make it through without you around. No, I'd never make it through without you around.
It's a fun little video, and with a serious intent. If all those few dozen scenes, you could imagine that some of them actually could play out backwards. It's possible to ride a bike backwards, or drive a car backwards, or a dog perhaps to be trained to run backwards. But some of the situations are clearly not possible to go in reverse. And it's interesting to think of what distinguishes those situations from the other ones, and what is it that really is fundamental to our sense of time being an asymmetric phenomenon. So time is symmetric and reversible at the level of individual atoms, but with a large collection of atoms, an arrow of time is apparent, and the question becomes why. To answer this, we get into the idea of entropy and probability. Imagine someone tossing bricks on the ground. Which would be more likely to see? The most improbable one, of course, is an ordered array or pile of bricks. A disordered pile is more likely. And the point here is that one ordered pile of bricks is one outcome. There are many possible ways to have a disordered pile. So the more probable event is the one that's more likely and that there are many of. Things get messy as time passes. The world gets messier or more disorderly. That's pretty much familiar from everyday life. We can clean things up, but that takes effort. It just doesn't happen by itself. And so disorder in the universe more generally increases with time. Disorder is entropy. Disorder is measured by entropy, and that increases over time. And this is related to the second law of thermodynamics, which says that disorder or entropy measured mathematically increases with time in systems that don't have outside interactions. Entropy grows, and that growth is related to all the aspects of the arrow of time: life and death, biological evolution, memory, the fact that we have cause and effect, and the flow of time itself. Without an arrow of time, the universe would be in equilibrium, with everything static, and there would be interactions, but nothing would ever appear different or change. The mathematics and physics of entropy was defined by Ludwig Boltzmann in the 1870s. He said that entropy essentially counts the number of ways we can rearrange a system without changing its basic appearance. Entropy clearly exists in biology, and it's worth asking, because at first glance it seems that biology violates the trend of increasing entropy, since biology is a high level of organization of chemicals in a coherent living organism. But if you look at it in detail, as in this flowchart on the left, the organization of the chemicals in biology depends on utilizing energy from the sun. You don't get something from nothing. And life, of course, metabolizes and releases heat and waste products which are disordered and disordered forms of energy. When living creatures die, the organization is lost and the entropy increases again. And these principles apply from evolution on a scale of species as well as individual organisms. So while it seems to violate entropy, biology in practice does not violate this tendency towards increasing disorder. And if we're trying to put all this together, we'd say there are many more ways for something to be disordered than ordered: the messy bedroom, the shuffled deck of cards, the scrambled egg. With interactions among particles, disordered states are more probable, more likely for it to be messy or shuffled or scrambled. And as time passes, things get increasingly disordered towards the most probable state, and that is the fact of entropy increasing. The room gets messy, the card deck gets randomized, the egg gets more uniform. Also, as time passes, disorder or entropy is very unlikely to naturally decrease. We would never spontaneously see the room get tidy, or the cards get ordered, or the eggs unscramble. To use the specific example of a deck of cards, if you started with a completely ordered deck and shuffle and shuffle and shuffle again, obviously the cards will get mixed. And even after they're well mixed, you may see sequences of 1 or 2 or maybe even 3 or 4 cards in numerical order. But you're very unlikely to see 7 or 8 cards in numerical order. And you would never see the deck, no matter how often you shuffled or how long you did it, rearrange back into a fully ordered deck. The arrow of time, therefore, reflects the universal trend towards higher entropy. And to maintain or restore order in a physical system, or a biological one, requires work to be invested. So let's look at an overview of the time sense. There are entities or objects in the universe that have an arrow of time, and some that have no arrow of time. Single atoms are outside the arrow of time. They do not have any unidirectional sense of interactions. That's also true of black holes. Within the arrow of time, we have all the assemblages of lots of atoms, which show the tendency towards disorder statistically and over time. And within that, also sentient life. And that's the end of this topic.